I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism podcast, an exploration of the past, present, and future of material science. My name is Taylor Sparks, a professor of material science and engineering at the University of Utah, and I'm joined, as always, by Andrew Falkowski, my co-host. And today we've got a special guest. We have Qichao Hu from SES AI. Qichao, how you doing?
Good.
So,
everyone.
SES AI is a battery company, and people who have been listening to this podcast know that we are interested in batteries. We've talked about it before, and we get a lot of requests for an update. They want to know about the latest and greatest on solid state, on lithium air, on metal, right? They want to know what's the current state of art, and we figured who better to bring in than an expert who's actually working in this area. And I just realized that Qichao and I were actually both PhDs from Harvard at the same time. We somehow crossed like ships in the night and didn't know that each other were there. I think you were over at the MIT campus around the time that I arrived, but we both got our degrees basically from the same group of people there at Harvard, which is kind of fun. And then you have since dove into this world of batteries. I saw on your LinkedIn that you were from the ashes of A123. So people might remember the A123 battery company was like the lithium iron phosphate that came out of MIT. You want to talk about your journey and how you went from a PhD in applied physics to being where you are now, working on batteries?
Sure. So back then, this was 2007, 2008, and then the Department of Energy back then gave a lot of funding to support renewable technology back then, and then including solar, batteries, and water purification. And we're both at SES, School of Engineering and Applied Sciences. Almost no one was not working on a project that wasn't related to one of these energy technologies back then. So I was at Harvard for the first year and a half, and then I was doing solar photovoltaics projects. But then at that time, MIT got way more chunk of that DOE funding than Harvard did, because most of that funding went to engineering projects, and Harvard tried to be like MIT with engineering, but couldn't. And MIT was still way better in engineering. So after a year and a half, I moved to MIT and then worked on battery projects. And that was the beginning of this journey on batteries. Originally, the project was funded by oil and gas companies to develop this high temperature battery that could be recharged downhole. So when you're drilling downhole and then you need to provide mapping information on the nearby natural gas reservoirs, oil reservoirs, you need to have sensors that were powered by batteries downhole. And then those were primary batteries, non-rechargeable. And they needed a battery that could be recharged. So you don't need to pull the whole thing up just to change a battery. So that was the original thesis for the battery.
Okay. So you got involved how? Like once you graduated, like you immediately started the company, or did you go and work for a while first on this outside of your PhD, or what was the process like?
So I started this company even when I was doing my PhD. For me, I wanted my PhD to be the R&D of my startup. So even about 9 months before I graduated, I incorporated SES.
No way. That's awesome.
Solid energy.
And at the time you were working on solid state batteries and then eventually transitioned over to lithium metal. Do you think you could give maybe an overview and comparison between the two and why you ended up making that switch?
So originally the technology was solid state lithium metal, and then lithium metal is one thing that we have not changed. We've always wanted to build a high energy density battery because high energy density is an area where there's a lot of room for innovation. If you do the lower energy density ones, then it's more competitive. So for a new technology, a new company to compete, we want to focus on the high energy density market. So back then included oil and gas, the downhole drilling. Back then, drones and EV were not so big. Drones were definitely very small, but EV was beginning to take off. This was 2012, and so that's why we wanted to focus on lithium metal. And then originally it was solid state lithium metal because we wanted the battery to be safe at high temperature. But eventually we dropped the solid state because we also wanted the battery to not only work at high temperature, but also room temperature, low temperature.
Gotcha. And just for listeners who aren't aware, can you compare, when you say lithium metal, what do you mean in terms of a battery versus maybe what people are familiar with a conventional lithium ion that's in a phone?
Yeah, so the difference between a lithium metal and a lithium ion is really on just half of the battery. The cathode half is basically the same, but the anode half in a lithium ion, you have graphite or silicon carbon. But in the case of lithium metal, you have just pure metallic lithium as the anode. And the benefit of that is you can achieve much higher energy density per weight and also per volume. And so you get that benefit.
So for another episode that we were recording recently, we were looking at large-scale grid storage, and we've been hearing about iron air, which is a sort of old technology, and there's a renewed interest in going back to that because of costs. What's going on there? Are you familiar with what's happening in that part of the battery world?
A little bit, and grid is really taking off quite rapidly, and the requirements are quite different. The emphasis is not so much on energy density, but it's more on cost and availability. And the cost in that market has really come down. So lithium ion, obviously, and also once you go to grid, it's not like a car or a phone. You don't really have that space and the weight constraints. I mean, people use pump hydro, right? Like so that solves the problem. So you don't have once you don't have that weight and space constraint, then you really have a lot more possibilities. And then also pump hydro is domestic. Right. So also, if you add that geopolitical aspect, okay, lithium ion, but most of that is imported, and then there's a big geopolitical push for domestic and decoupling from some of these global supply chains. So iron air, pump hydro, there's a lot of these maybe older technologies, but they're cheap, they're available, and they're local, and you get that supply chain security.
So returning back to kind of what SES AI works on, or at least in the early stages, you put a lot of emphasis into the electrolyte itself, whereas I see in the research a lot of people are interested in developing new cathode materials. Why so much emphasis on the electrolyte, and why the shift from solid state to a liquid or polymer electrolyte?
Yeah. If you look at a battery, the cathode and the anodes are more or less fixed. The room for innovation and the need for innovation in cathode and anode is relatively less than in the electrolyte. So the nice thing about electrolyte is you can have the same cathode and the anode, and for different applications, different customers, you can fine tune the electrolyte and then get very different performance. So in the battery world, you have what's called dry cells. And the dry cells basically are just the cathode anode. And then you will have that fixed for EV market, fixed for grid utility market. And then you would just fine tune the electrolyte if the customer is in like a cold climate or a warm climate, and then you will fine tune that. And then to the customer perspective, you can really optimize the performance for that. And then the reason for pivoting away from solid state, and then we made a decision back in 2015, it was more driven by market. So we were one of the companies back in 2010, 2012 that first really pitched for solid state. And then we realized around 2015, why do we keep pursuing solid state? And all the so-called promises of solid state were either not true or they weren't meaningful. So solid state promised high energy density, but that's not the case. So solid state itself doesn't give you high energy density. It's the cathode anode combination that gives you high energy density. Solid state promised better safety, but that wasn't true. Solid state, in a lot of cases, couldn't pass some of the nail penetration, high temperature tests that a liquid electrolyte could pass. So the benefits of solid state just were no longer true. But the disadvantages of solid state definitely is more expensive because the manufacturing process was much more complicated. So we decided to pivot away from that because why would you want to spend more developing manufacturing process for a new technology that's worse in everything? It was worse. So it was worse in power density. It wasn't better in energy density, and it wasn't safer. So there's no benefit, but there's clear disadvantage. So we dropped that in 2015, and I think that was the smart decision to do. And then we focus on liquid because the benefit of liquid is you can actually make it safer than solid state. You can improve the energy density and power density even more than the solid state. It's a lot easier to fine tune a liquid than a solid because when you're in a solid state, most of the issues are with manufacturing process.
Oh yeah.
So even if you were to improve the materials, you're not seeing the benefits at the cell level because there is a ton of engineering manufacturing process challenges. Whereas in the case of liquid, the engineering manufacturing process is fairly straightforward. And then you can fine tune the salt, the solvents, the additives, the formulations, and then get very clear benefits. So since we pivoted away from solid state back in 2015, we actually got a lot more customers in drones and in EV applications.
So I can totally second this. I cut my teeth working in ceramics at a place called Ceramatech, where their bread and butter were like solid oxide fuel cells, solid oxide electrolyzers, where you have to have these thin ceramic membranes and you have to stack them together actually into these stacks and controlling like coefficient of thermal expansion and cracking. And it's just a nightmare. And those exact same challenges will come to bear if you're going to try and make a thin ceramic membrane for a solid state battery. So my advice to students is always only use ceramics when nothing else works, right? Like they're amazing and they do the job when nothing else works sometimes. But if you could get the same battery performance that you need for a product by just controlling the electrolyte in a liquid phase, like you're going to have a lot of advantages. And I'm not surprised to hear that that's been the case for you and that you found customers with that approach.
Yeah, this reminds me of so my background's in the nuclear industry, and there's a lot of these startups right now pushing for new reactor designs and different approaches to the design of the reactor and the utilization of the fuel. And these have a lot of potential merits and promises with them. But the big uphill challenge is that there's huge regulatory costs and development costs associated with these. If you're going to introduce something new, you have to go through quite a bit of testing to prove that it's safe, and you have to go through quite a bit of work to develop the manufacturing capability to meet it. So is this also a component here where it's liquid electrolytes have a existing supply chain, they're well tested, and we know how to test them, and we know what sort of failure modes to look out for and account for, and that just made it easier to work within that space, as opposed to trying to develop all of this out for solid state?
And also, I mean, I think if solid state can deliver better performances, better safety,
Yeah, that'd
then
be one
maybe
thing, right?
Yeah, then maybe the manufacturing work is worth it. But solid state is not able to deliver anything better. Then why invest in all these manufacturing process work?
Yeah, I'm getting curious about that. So I'm not really a battery expert, but there's still quite a lot of companies working in the solid state space. And I'm sure maybe some of our listeners might be working in that space too. So
Yeah, yeah.
surely there must be some sort of advantage to them, or maybe not advantage, but use case for them.
So there's one caveat, and then in the industry, when people say solid state, they mix solid state for the electrolyte and also advantage in the anode.
Right.
For example, they would have a sulfides or oxide lithium metal and say that has higher energy density than the lithium ion graphite. So then, in that case, yes, there's benefits of that, but that's not because of the solid state. It's because of the anode that we're using. And then you could totally achieve that energy density by using a liquid lithium metal. You will achieve the same energy density benefit, and there's no need to go to a solid state lithium metal.
Gotcha.
So let's talk more then about tools that you're using to design this, because it's tricky. On one hand, the ceramics are hard because you have solubility limits dictated by thermodynamics, and you have thermodynamics with liquids as well, but typically you're getting much larger windows where you can have solubilities. So your design space really takes off, and that's where it becomes useful to have design tools. So do you want to talk about some of the tools that you've put together? I see them deemed as the sort of molecular universe and how that's been helping you.
Yeah, and I think so if you look at a battery, and then in our case, when you have a liquid electrolyte, we focus a lot on the electrolyte space, the electrolyte design space, because that has the highest return on investment in terms of how much work you need to invest in the electrolyte design and how much impact it will have on the performance. So in terms of the design tool that we have a whole suite of design tools going from single molecule level. So this could be a salt, a solvent, additive, single molecule level. We use density function theory computation. We have the full just quantum mechanics computation, which takes a long time. We also have machine learning prediction for the density function theory properties. So we can use that tool to compute and also predict the single molecule level properties. So these are like melting points, boiling points, flash points, homo, lumo, the basic single molecule level properties. And then we have the formulations. So now you start to mix different salts, different additives, different solvents. And then at the formulation level, then we have molecular dynamics force fields. And then we use that to predict formulation level properties. So these are like you mentioned, solubility, viscosity, conductivity, and other properties. But these are bulk properties. And then we're still so these tools, the DFT and the molecular dynamics, these are pretty straightforward. The key is really being able to do the prediction accurately and also at large scale. We can't just do this at 10 or 20 a day. We need to do hundreds of thousands and millions of these a day. And then at the interface level between the electrolyte and the cathode anode, then that model is more complicated. That model is still being developed. I think we are at the forefront of developing and understanding how to model the interface properties between the electrolyte and the electrodes. For example, the SEI, because now you have a mix of chemical reactions, electrochemical reactions. The thermodynamics now is can be predicted, but then the kinetics is now really complicated. So that we are developing. And then at the cell level, it's even harder to simulate all the reactions that happen inside the cell. So what we have is we rely on machine learning models. So at the single molecule level and the formulation bulk properties, we have these models. But once we get to the cell level, we use machine learning models. Basically, we treat the battery, mostly the interface, as a black box. We don't understand it, but then we have the input and the output. We know exactly what the inputs are, the cathode materials, the anode materials, the electrolyte formulation, and then we also have the outputs. We have the cell level properties, both during cycling and also during formation. So we have the input properties and we have the output properties. And then because we have our own wet labs, we have autonomous labs, and then we collect a lot of these data, the input and the output. And then once you have a lot of these data, you can make estimations about how this black box work. So now we have a simulation of the black box, even though we we have no idea how to simulate the black box. But just by knowing the input and the output, now we have a fairly accurate simulation of the black box. So that's a suite of tools that we have from the single molecule level going all the way to the cell level.
And from my understanding, this was developed initially in-house to facilitate the design of different electrolytes, and you found some pretty good success there. Is that right?
Yes, this was originally developed for lithium metal batteries. We had 6 car companies that were investors in SES, and then 3 of them we had pretty large joint developments with. And then they wanted us to basically develop lithium metal for EV applications, predict any incidents, any issues there might be under a variety of different testing conditions on the road. So we built this tool for that. And then last year, 2025, and then EV market collapsed 24, and then 25, the other companies in the battery space and the car car industries, they became almost less interested in our batteries and more interested in the tool. So we started offering this tool last year.
Is that still the case? Like, are you still then are you trying to do both? Are you trying to be still a hardware company for batteries and a discovery as a service sort of company?
So I think if we are a private company, and then if we don't have like quarterly revenue targets, all that stuff, we would love to focus on just the discovery, on just the tool.
Sure.
But because we have to meet the financial targets, so we still do the hardware.
I see.
So we still build the batteries that contain these electrolytes discovered by the tools, especially for drones.
All right. So thinking about this then as a service that people could use, tell us how they access it, what type of inputs they'd be providing, what they can expect as an output. Tell us how it would actually be used.
Mm-hmm. So we have cloud version and also on-premise. The vast majority of the users use the cloud, and then we have some enterprise customers that would pay, and then we would do on-premise deployment. And to me personally, I think the cloud version is really powerful because the users get access to. So we have 6 modules. The first one is called Ask. So it's a agent, and then there is a LM behind it. But then we also put all the literature, both public and also private, that's relevant to electrochemistry, to organic chemistry, to batteries behind it. So the answers that you get are more relevant and then deeper than, say, if you were to ask just ChatGPT's deep research. So it's way deeper. And then we have the single molecule database. So a user could ask a question about, for example, I want a new formulation that can improve my ESS battery performance, low temperature performance from 6,000 cycles to 8,000 cycles. And then it will give you several guidance, directions, approaches for how to do that. And out of those approaches, it will list out the molecules that the industry currently uses. And then you can take those molecules, and then you can go to this database and then find friends of these molecules. So, for example, currently these molecules can only do 6,000 cycles. So these molecules have some good properties, but some bad properties. And then you want to keep the good properties, but you want to change the bad properties. So you want to find friends of these molecules that have the same good properties, but have better of the bad properties. And that's how we find new molecules that can replace. And then you go into this formulation, and then it would help you predict the bulk property, bulk properties. And then you go to design. So you can plug the formulation back into the cell, and then it will tell you, okay, it would actually improve the cycle life, or actually it would hurt the cycle life. It would maybe improve the cycle life, but then hurt the low temperature performance, or it will improve the cycle life, but hurt the discharge rate. So it will give you these design guidance, And then so you would know all these things without even building a cell. And then you get to predict. Then it's once you actually build a cell, and then you go through all the validation testing, and then, for example, 6,000 cycles to 8,000 cycles, that will probably take 2 to 3 years. You don't want to wait that long. So the predict, you can take just the first 1 month or 2 weeks of data, and then just based on that, you can predict the end of life. You don't need to wait 2 years, 3 years. You just need the first 2 weeks of data. So that will save a lot of time. So that's the what the users would have access to, and then behind the scene, what's also valuable is we get to see, obviously anonymously, what questions people ask, and then we also get to see for those questions what kind of molecules and formulations they choose. So all anonymously, and the benefit of that is basically we train this black box. This black box is called scientific intuition, and there's a lot of things in the battery domain and also in other scientific domains that are not linear. Like you cannot make a mathematical equation to model those things, and a lot of these are based on scientists' just intuition. So the way we can capture that is just by taking what question they ask and what kind of answers they like.
Oh, that's
And
cool.
that input output, that helps us train this black box in between. So it's getting smarter and smarter by itself. We have a feature where we let users, when they ask a question, and then and then the model would recommend top 100 molecules. And then so we let the users do thumb up, thumb down, and then so that ranking actually changes. For example, initially your favorite molecule maybe it's not in the top 100, but then after a few iterations, say people that ask that type of questions, they're generally interested in a certain type of molecules, and then after a while, those most relevant molecules actually get moved up on the ranking.
This is cool. So in large language models, right, this is very, very relevant. This is how a lot of the fine tuning is done, is through reinforcement learning on how people interact with the model. There's been quite a bit of work on like essentially the concept, like there's this allegory of like the stone soup, maybe you're familiar with it, right? So there's like somebody's cooking a stone soup, right? And like the concept is like when people want to learn what it is, right, they ask. Right now it's just like rocks in hot water. But then when the villagers come, they basically trick them into adding the ingredients to the soup. Like somebody's like, oh, it'd be better if you had carrots. So that some of them bring carrots. And then, oh, if you have potatoes. So this has been applied to large language models to essentially say like the language model's okay, but it's sort of like the stone soup where there's nothing in it yet. It's a flexible model. Mm-hmm. It's the expertise that users bring to it that really adds value, which is kind of what I see happening with yours. People ask a question about batteries. You have this great tool that looks like it finds based off of latent space proximity, other nearby components, but ultimately it's how they interact with those suggestions, what they select, that then improves your model's ability to provide future reasoning for other users of the system. Very, very cool approach. I think that's a clever thing you're doing.
Yeah. We're really trying to capture that scientific intuition, because we do have a lot of scientists that kind of complain because the way these models think about finding molecules is very different from the way a senior scientist thinks.
Sure.
Like if you give just a molecule structure to a senior scientist, that person is going to know just intuitively, without doing any math, without knowing any properties, just by looking at that structure, if it's going to be good for high temperature or good for low temperature. There is that intuition. Whereas the model just previously just has to do a basic calculation and then list out the values. Very non-intuitive.
Yeah, I have to think that also providing all of this battery-specific data can enrich kind of the context from which it can pull from, as opposed to just asking one of these models or doing one of these things in isolation. It sounds like you have this large suite of not only simulations you can do, but ways of generating data at different hierarchical stages of the battery, whether that's at the molecule level or at the larger cell level. An interesting question. So what is the path forward in terms of developing this, right? Is it running more simulations, or is it actually starting to take recommendations from the model and actually see if they, bear fruit?
So I think the cell level, this scientific intuition is definitely a big focus. We've basically completed the mapping of all the battery relevant properties of all the battery relevant molecules. I don't think there's like more molecules that we need to map for battery application. So we've mapped those properties, but still, one of the most challenging things in battery, and I think in any scientific domain, is taking a device level performance requirements and then map that onto the most fundamental level properties. For example, a customer wants, I want a longer range battery. But what does that mean in terms of what molecule I want to look for in the electrolyte? That mapping, no one knows.
It's not like a one-to-one. It's a highly
yeah,
nonlinear relationship there. And that's not something
yeah.
that's happening in academia. Like that's where I spend all my time, right? And I don't see academics
Mhm.
even trying to do that. I don't think they have the data. They don't have the manufacturing capability. They don't have the devices to do that. But that would add a ton of value. Do you think you guys are close to being able to provide that? Like, how confident are you in that? In other words, what are the limitations of this approach?
I think it's possible, and I think we're quite close. The limitations is just a lot of high quality, like really high quality data throughout the entire workflow. For example, that specific question, if a customer wants a specific battery, like a performance at the battery level, and then to map that all the way to the additive level, solvent level, then you really have to have a workflow that connects all this. You can have some data at the bulk properties, and then some other data at the molecule level, and then some other data at the cell level. Like you can have fragmented pieces of data from here and there at different levels of the workflow. Then it's really hard to build that connection. You have to have very high quality data, basically that same batch of cell, and then the materials, the electrolytes, the bulk properties of the materials used in those specific cells, and then the molecules used in those specific materials. So, so I think real data, actual data,
Yeah, I agree.
matters a lot.
That's the magic, I think.
Are self-driving labs the key to generating that data? Because it's just a massive search space, and even with good researchers, these things just take time, and people aren't going to be working overnight and stuff.
Yeah, self-driving lab is definitely the key, because we found, and then it's not just us. There are larger battery companies that have data going back 10 years, 20 years, and they try to leverage that data. But then it's like, okay, someone collected this data 5 years ago. That person is not here anymore, and then no one knows how that person collected the data, and that condition, the format is totally different from how someone else collected that data. So you have a lot of data, but then it's actually harder to organize, make sense of that messy fragment data. Then might as well just get like a self-driving lab, autonomous lab, and just run new experiments, everything under control. Just collect new data. Collecting new data is almost easier than going back to other people's old lab books, trying to make sense of that.
Yeah, I see this problem a lot where it's like, oh, we have all this data, and it's just disparately organized, imaged under various conditions. Nobody really knows the provenance or the pedigree of the data.
It's like anything but AI ready.
It is really interesting that a lot of the promise of self-driving labs is actually just redoing a lot of old work
and fixing the metadata pipeline where we capture everything, unify everything along the way.
Yeah. I mean, the self-driving lab is definitely a key. And then especially, for example, we come from a lithium metal background, right? But now we're trying to train molecular universe, say for lithium iron phosphate. We don't have a lot of lithium iron phosphate data. And then, so having self-driving lab, we can collect new, high quality, consistent, very clean data on lithium iron phosphate, and then use that to train our models.
Well, we've got two questions for you as we round out this episode. First is I'm just kind of curious from your perspective. You've gone from like seeing a couple sort of variations of battery research where there's been hype and interest and funding, and then it's evolved. So clearly the nature of materials discovery is changing, and it will continue to change, right? The stuff that I was, was being hyped 20 years ago, nano everything when I was an undergraduate, that's come and gone, and it's quantum and it's AI and these sort of trends come and go. But I'm curious from your perspective, knowing that trends will come and go and that this nature will change, what should scientists be doing now?
I don't know if scientists will have a job in the future.
It'll be a different job, that's for sure. It won't be the ones that we had.
Yeah, I think a lot of the workflows will be automated, and then so it's like batteries or refrigerants or like whatever the scientific field. I think once you understand the workflow and you can automate the workflow, then it's about just filling the workflow with domain relevant data. And then so I think we still need a scientist to figure out the workflow, because like Claude, and then there are these big tech companies, they're trying to come out with these skills that try to automate workflow, but that's too general. Like you cannot expect to make scientific discoveries by using a generic workflow. The scientists still need to develop very domain, even topic specific workflows, and then identify the type of data. And then once you identify the type of data to fill in, then you can have self-driving labs to just collect the data. So I think we still need scientists to figure out how to automate the workflow, and then also how to ask a question like that prompt, and as detailed as specific as possible. I think those will still be the key roles for a human scientist.
And then the final question we have for you is then, what will SES look like in the future? How will you guys plan on adapting to the changing sort of research landscape?
Basically, the two roles I mentioned earlier, we're hoping to be like a one-stop shop for the other customers that want to do this. I think now we do a good job in batteries, but we plan to expand to other domains. And then so say a chemical company comes in and wants us to develop a new pesticide, and then so we would spend time with them, understand the details, and then automate the workflow and identify the type of data, and then design the autonomous labs to collect those data and then fill in that workflow.
This sounds like a really cool tool, and I'm sure a lot of people might be interested in using it. Is this something that they can access through your website? Is this some sort of hardware that they actually purchase? What is use for this look like, and how does industry or other people who are using it contribute then to its growth?
Mm-hmm. So people can use it at molecular-universe.com, and then it's free to use. So anyone can register and then use and then contribute to the improvement and evolution of this scientific intuition, this tool. And then for users at companies that may have policies against using such cloud-based tool, we also have an on-premise deployment where we would install the latest Molecular Universe software database inside a server, and then provide that server fully air-gapped to an enterprise customer. So both cloud, molecular-universe.com, free to use, and also on-premise.
How do you handle proprietary data?
So again, for the cloud-based version, if people don't want to upload proprietary data, then we can provide the on-premise deployment. So for on-premise deployment, it's fully air-gapped, and then people can upload their own proprietary data, and then we will not be able to see anything.
Gotcha. And does that data work within the system? So the same models that are operating on the preliminary database, right? Like if I had some battery data, I could use those same models on that, and my proprietary data improves those models in some way.
Yeah. So if a user has a proprietary data, and then obviously if you were to incorporate that into the cloud molecular universe, you would improve the general molecular universe for everybody. But then if you were to input your proprietary data to the on-premise deployment, then your on-prem molecular universe will get really good and then will become customized to your data. For example, you have a lot of LFP data, and then someone else has a lot of sodium data. Then your on-premise molecular universe will become really accurate at LFP, and then that other person's on-premise molecular universe will get really accurate at sodium. So the individual molecular universe will also evolve and then get really good at the specific user's tasks.
So I'm on this website right now, molecular-universe.com, and we obviously shout out to SES AI for you guys for sponsoring today's episode. Disclose that, but this is a cool tool. Like, just I'm looking through it, and I'm actually learning a fair bit just looking at the different clusters of materials, whether you're looking in the solvent space, additives, salt ions, electrolytes. This is a really great, just like a resource in terms of almost like a review article of content here to sort of look through and see what's being explored, even if you weren't going to use it for the formulation and the design aspects. So definitely encourage people to take a look at this. This is pretty rad.
And those molecules are suitable for obviously batteries, but we also have a lot of people using them for sugar, vitamins, food, nutrition, coolants, and other applications that also use small molecules.
Okay. Well, thank you so much for joining us on today's episode. We learned a ton. I know that I certainly did. And more broadly, I want to say thanks to SES AI for sponsoring today's episode overall. It's clear from today's conversation that these are some amazing tools. And I hope it's clear to our audience that if they've ever felt frustrated in today's battery development process, that they can now consider these as being the right tools and the platform to help them accelerate the discovery workflow. We think that Molecular Universe is a great example of a product that was built by material scientists for material scientists, and specifically their new MU3's launched agentic system, Starseeker. It's going to be even more powerful, and we hope you go try it out yourself. Hey, we want to remind our listeners that today's episode is sponsored by Momentum Transfer. I've said it before, but having access to synchrotron data for powder X-ray diffraction is an absolute game changer. The resolution and intensity allows you to access information about your materials that are just not accessible with lab X-ray. And now with this company, you can get access to that synchrotron data without time-consuming proposals, waiting for them to get approved, sending somebody to go actually do the measurements. It's an absolute game changer. I love their business model. I hope you'll take advantage of it. And they've made it possible. In fact, if you go to momentum-transfer.com and you sign up, then you'll be able to get total scattering and PXRD measurements for 5 samples for free. You just can't beat that. So check them out.
The Materialism podcast is also sponsored by Materials Today. You can visit materialstoday.com to stay up to date on the latest happenings in the material science field and read some of the fantastic articles that they've published. You can also head over to elsevier.com to find out more about their journals, books, conferences, and related programs. And then lastly, thanks to the people that make the music for the show. Thanks for the listeners who reach out and suggest episodes. You can get a hold of us. We are materialism.podcast@gmail.com or the @materialism.podcast on Instagram or pretty much wherever else. We would love to hear what you want to hear next, so drop a comment, whether this is on Spotify or on YouTube or wherever you're listening to this. Leave a comment. I try and get to all of those. Send us a message on Instagram. We try and respond to everything because we appreciate our listeners. We love that you're out there. And with that said, we will wrap it up. See you, everybody.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.